Hello, so my name is Krish Gandhi, and today I'm going to be reflecting on the public lecture two that I attended. It was taught by Professor Brian Kennedy from the Georgia Tech School of Physics. So his lecture primarily discussed how um, discussed the 2025 Nobel Prize in Physics, which was given to John Clark, Michel Devoret, and John Martinis. Sorry if I mispronounced it, but yeah, it was based on their groundbreaking work on macroscopic quantum tunneling and energy quantization in electric circuits. So the main idea of the lecture basically saw how, um, sorry, the main point of the lecture was to look at like quantum mechanical phenomena, which we usually see in things like electrons, and other tiny particles that can be seen in macroscopic systems as well, and how it can be applied to those like superconducting circuits, for example, which would have billions of electrons, and why this is important for quantum technology, such as like computing, for example. But yeah, so during the lecture, Professor Kennedy explained the key physics concepts behind the research. So he discussed quantum tunneling, which is the idea that particles can pass through energy barriers even if we don't have enough energy to overcome them classically. And what's remarkable about that actually is that the tunneling effect, which is observed in a macroscopic system, can be applied to more than just the individual particles itself. So he explained the energy quantization in these circuits, saying that they could only absorb or emit energy in like discrete steps. So the usual like experimental setup would be seen in like superconducting circuits. That would be cooled to extremely low temperatures by measuring the system through like an escape to voltage state or something like that. I didn't really understand this concept too much, but that's what he was like talking about. But yeah, so he connected these discoveries to broader implications in quantum computing and quantum information technologies, which was pretty cool and like on the real world. But one thing I learned from the lecture that I didn't really know before is how researchers can engineer like these kind of circuits um, to like behave as like a single quantum object. So then you can see like billions of electrons to collectively show quantum tunneling. Like I knew a little bit about like quantum tunneling um like before, not too much. I haven't I don't know too much about like the whole concept, but I have like heard of basic things from TV shows like The Flash actually, and some of my other friends that are in physics. Um, so I had like a surface level knowledge of it, but I feel like this lecture was pretty cool because it kind of reinforced some of the knowledge that I didn't know. So like some of the knowledge I did know, for example, was that like this energy quantization is important to quantum systems because you can see how like you can apply it into things like circuits um, and like other real world experiments. But yeah, so that really sparked my curiosity a little bit, and I just thought it was really cool. And then the lecture kind of relates to my own area of study because I'm a bio major, so it's kind of hard to relate it to it. But like if you look at it from like a BME standpoint, you can like apply certain aspects of this to like prosthetics and like other like technologies that could be seen in like a biomedical point of view. So it's kind of cool because at the end of the day, like a lot of things in the modern world require circuits, and electrons are at the heart of circuits and making things work. So it was pretty cool that like you can kind of apply that to a bunch of different concepts and fields. So yeah. But after the lecture, like I did have a couple things that I was confused about and wanted to learn more about. So for example, I followed up a little bit by like just looking up a surface level about like things like superconducting qubits, which are important for many modern quantum computers. So I learned how these qubits rely on like the same principles that you'd see in quantum tunneling, that Professor Kennedy discussed. And I also saw how some of these researchers in maintain this kind of like information that I saw during the lecture. So it was kind of cool that I could like see how these challenges push like like the idea of like experimental physics to like new levels, right? So that was all like something cool to see. And then yeah, but like just in summary from like the lecture is Professor like Kennedy's lecture just like taught me a lot more about quantum tunneling and engineered systems and how all this is like important to quantum science and technology. So, and I did learn new experimental methods, and connected these to some of like the basic understandings that I had already heard of in like previous like just things that I would have seen in just life and um through physics fans and TV shows or whatnot, right? But yeah, so overall the lecture was really informative and interesting. As someone that's not too involved with like the physics world as a bio major, it did give me like a new like level of like appreciation and understanding in physics. So it was cool. I got to see information about the 2025 Nobel prize in physics and how it impacts other areas of science and technology. So I'm glad I attended. It was pretty cool. All right, that's it for me. Thank you.